Hello everyone. Let us look at another mode of sensing. In this particular case, we are looking at fluid sensing, in particular gas sensing possibilities. How one can detect gas instead of liquid that we saw in the earlier lecture. So gas sensing is little different. So where you need to measure the absorption changes here. So the density change is very small, right? It's already a rare environment. So the density changes are going to be very small. It's not that we cannot measure it. We can measure density change in air, but then the problem is the sensitivity is going to be low. So you are going to have very small change in the refractive index. However, gas molecules, they got their characteristics absorption, though the density is not high, but they have their own molecular vibration, and when you are illuminating with the right wavelength, you can create absorption to this particular molecules. So let us look at whether we can exploit our photonic circuit platform in order to sense this kind of environment that has absorption in it. So is there something special that we can do about this, right? So the basic principle of doing absorption sensing is to create high light matter interaction, right. So you want to make sure that the light interacts with the environment, right, as much as possible. So the reason for that is the longer the interaction length, the higher the absorption. So for that we use a gas cell. So this is where you can put in the gases, and what we have is spiral waveguides, right. So we saw these kind of spiral waveguide fabricated and SEM in the earlier lectures. So this particular cell could have such a waveguide, and the waveguide is going to carry the light here, right. And we can put a single wavelength source here that is absorbed by the gas present inside this medium, and because of the gas present inside the medium, you will see a change in the intensity there because it absorbs that. So based on this intensity change, right, you start with something very high, but then after going through the material, right, here the gas cell, your intensity might come down. So you are looking at what is the delta intensity change or the power change, or power absorbed by this, and this is directly related to the concentration that we have inside the cell here. So this is a direct way of doing absorption sensing, and this particular technique is called non-dispersive technique, because you are using a single wavelength source and just measuring the power output from this single source, right. So this is relatively easy to comprehend and understand. The other type of measurement requires a broadband source. What happens when you put a broadband source? So again the same gas would be there, right, and it goes through the gas cell, but then in this case you need a demultiplexer, right. So this is a filter that you want. So it is a wavelength filter, and you have filter outputs from lambda 1 to lambda n. So that is what you see here. So now in this case, right, you have a broadband source, and when you look at the actual spectrum, right, it will look something like this. So a particular gas is present, so it is absorbed, right. So this particular gas absorbs, it should have been something like this, right, but we have absorption there. So how do we get this absorption data? By looking at the spectrum, right, and that is why we need a filter and then coupling it out, and by looking at the outputs here, each output corresponds to each signal here, right. So we take this signal out here. So by looking at the power from each of this output, we can say that ideally you will have something like this, but then when you have a gas absorption, all the other wavelengths might be identical, but one of the wavelength will be lower. So that means when you trace this, you will see that this particular gas is now absorbed, and then we can relate this to our molecules. Right. So, whatever molecule present in the gas cell here. Okay. So, this is how we can do absorption sensing, and as I mentioned, the sensitivity depends on the intensity change to the concentration. The concentration gradient gives you how small a difference that you can measure from this. All right. So, let us see how sensitive we can make this. Right. And the light matter interaction, as I mentioned, is important here. So, this is a typical waveguide structure, and what you see is the electric field. So, this is nothing but E field of a TE mode, right, transverse electric mode. So, it looks something like this. So, you have electric field outside, only this much available, but you can see here most of the light is sitting at the center, right, inside silicon in this case. So, only very small fraction is available for interaction outside. So, whatever we have here will interact with the light here. So, only a fraction is available, but if the only fraction is available, the sensitivity is also going to be low. Okay. So, in order to have a very strong absorption, you want the light to be outside, propagating in the low refractive index medium. So, this is air, right. In this case, this is air and this is silicon dioxide, and here we have silicon, right. So, this is air, as I mentioned. So, you want the light to be sitting outside, right, interacting with the rarer medium, and there we use a structure called slot waveguide. So, this is called a slot waveguide, and the slot waveguide confines the light outside the core, right, the solid core, and this allows us to make a very good light matter interaction. So, that means you are going to interact with this volume very strongly, right, the air or any gas that we have outside very strongly, right. This will help us in improving our sensitivity. So, by how much? Let us look at how good sensitivity we could have. So, what you see here is the interaction length, right, and different fill factors, right, effective field fraction, right, how much of light, this is nothing but how much of light is outside the waveguide. So, effective field enhancement, right. So, when you have about 13-14 percentage, right, we have the sensitivity rather low, right, and this is assuming you have a propagation loss of 2 dB per centimeter for this waveguide. So, this is a basic loss that you have. On top of this, you will have alpha absorption loss, and that is what we are looking at. You can see here the lengths are in centimeters, is rather small structures. So, when you have a field fraction of more than 30% out, right, then you can get very high sensitivity for a very small length. We are talking about only 1 centimeter length, okay, and this is done for carbon dioxide gas, and how sensitive these things are. And what if we take the maximum sensitivity, right, and look at the loss of these waveguides alone. So, obviously, you want low loss waveguides, right, because as I mentioned, your total loss is between the base loss, that is the waveguide loss, plus the absorption loss, right. So, if I were to draw this waveguide, right, so your waveguide will have the scattering loss, right, the scattering loss that we have, and the absorption loss, that is from here, and then you will interact with the gas molecules outside, and that is from the absorption loss. So, when the waveguide is propagating through, right, the length, it will have absorption from the or scattering from the waveguides and absorption outside, right. So, that is the total loss that we have, and you want to make sure this base loss. So, that is what this 2, 5 and 10 signifies. So, when you increase this base loss, right, the delta loss that you get is not going to make a huge difference. Okay. So, you can see here, even before traveling 1 or 2 centimeters here, the sensitivity goes down, right. So, you have very poor sensitivity for lossy structure. So, that is why we always try to reduce the propagation loss. The propagation loss are unwanted, undesirable characteristic of any waveguide system, but you cannot avoid those because of technology limitation. It cannot be 0, you can make it the lowest number that you could have. So, this tells us that when you are doing absorption sensing, make sure that your propagation loss is taken care. So, what sort of concentrations we can measure? So, that means how good these structures are, right. So, the optimum length that is required depends on the waveguide loss and the absorption that you have. Okay. So, when these things are large, you just need very low propagation length. Okay. So, you want to make sure your alpha waveguide should be kept as small as possible. All right. So, let us look at few scenarios here, right. If you want to measure 50 ppb, this is parts per billion. So, for a 50 ppb, if your field fraction is 34% outside, that means 34% of light is interacting with the gas, and when you have a 2 centimeter per dB per centimeter loss, you just need about 2.2 centimeter long waveguides. This is very small, right. When we say 2.2 centimeters, right, you no need to measure, right. This is 2 centimeter. So, we all know that we can make a very compact waveguide system, right. So, we can squeeze this within some hundreds of micron, right. So, you can really squeeze this in about 200 300 micron space on the chip that you have. And when you have some relaxed concentrations, right, 500 ppb, 5000 or 50,000 ppb, your length requirement goes down, right, because the concentration that you are looking at reduces. You can look at very short distance that you need. All right. So, this is a very interesting way of implementing such absorption spectroscopy on chip. Okay. But in order to do this, we have to make sure that we have this the waveguide that we talked about, right. So, that is your let me go back. So, your slot waveguides are fabricated and we are able to achieve this kind of waveguide structures, right. So, let us look at how we do this kind of waveguide structure. So, this is an a cartoon that shows the simulation of such a waveguide excitation. So, what you have here is a strip waveguide. So, that is a wire waveguide, right. So, the wire waveguide is here, a simple wire waveguide, this silicon waveguide. Let me, it is too small. And then on the output you have a slot waveguide. So, slot waveguides are like this, right. So, we go from a simple wire waveguide to a slot waveguide, and this is the structure we do, what we call the split and combine technique. So, when you do this, this is this FDTD simulation that shows light is getting split into 2 arms, and then when you combine it, it creates a slot mode here. So, you start from a very simple wire mode here, which is the E field we see here, it is a slot mode excitation. And actually we can cut at various locations and then see how this combining happens, right. Starting from position A, you can see these two modes are separated. So this is where we need to look at our coupled mode theory, right. So there are two waveguides that are parallel waveguides fairly far apart, right. So 400 nanometers. So when the waveguides are far apart, then these are all individual normal modes, they do not talk to each other. As the waveguides coming closer and closer, then you talk about coupling now. So then your total solution is not anymore to normal solution. So you have super modes, right. So this is something we discussed in our directional coupler, if you remember, right. And coupled mode theory also a lot of discussions on how these modes could get coupled, and that is exactly what we are applying here. So let us look at how the mode evolves as you move. So at section B, they are coming closer and closer, right. You can see already there is interaction starting to happen and the gap is going down. The effective index increases because this is a system mode, okay. So they are coming really closer, right. Again this is a system mode till section C, right. So your effective index is increasing, that means the mode is here coupled, okay. And then when you confine the light outside, right, in air, the refractive index, the effective index reduces. See, this is the beauty of this whole excitation. All along your ineffective was increasing. Why it was increasing? Because you are bringing the two waveguides closer to each other. So this is exactly what we discussed in our directional coupler, right. So you will have individual modes, but then when you bring them closer and closer, you will have system modes, right. And these system modes or super modes will have higher refractive index than the discrete normal solutions that we have in the waveguides, and that is exactly what we see. So these are all coming closer to each other, right. They are fairly far apart, they are completely isolated. When they are coming closer, you can see it slowly increases, but then the moment it achieves this the condition for the slot excitation, the mode jumps out, right. So as we all know, the effective index depends on where the light is sitting. So in this case it is sitting outside, so it is sitting in air, right. Because of that the effective index goes down, right. This is one way of confirming whether you have excited the slot mode here, and it even reduces down when you bring when you reduce the width of this. So this is also important to notice that you are squeezing the light into it. So you are changing the width of the rails that you have here. By changing the width of the rails, you are pushing the light even outside, right. So now the effective index is even lower, all right, and it is very highly confined. So this might be a little bit confusing, right, coming from our waveguide understanding, right. So when you have higher refractive index, light will be confined inside the core. So this structure is very different, right. So where you have two high refractive index separated by a low refractive index medium. So you are squeezing the light, right, in order to push the light outside. So what we mean by that is you have two rails, right. So two solid waveguides that are in cutoff, right, but then putting these two cutoff rails together, you create a propagating solution, right. So there is a continuity equation that you need to make sure that epsilon 1 E1 should be equal to epsilon 2 E2 between these two systems, and once these two E fields are equal, right, when the E fields are together in that boundary that you have, then the energy just jumps into this cavity or into this trench that you have. So then you can effectively use this confinement, and let us look at how efficiently we can couple this to the waveguide. right. So, when you have this two splits, and then when you are combining those, you can excite this mode with near unity coupling efficiency. So, nearly 99% of the light could be coupled, right, when you have this gap of 100 nanometers, right. So, this is a very very efficient way of coupling light into a slot mode. So, now the question is how do we make this, right. So, we go through the fabrication process here, which is something we already discussed in detail, but for completeness I want you to follow this through as well. So, we take a silicon on insulator waveguide wafer platform. Here you have silicon dioxide. We transfer the pattern to photoresist. This is using lithography, right, and wherever you have open area, we etch those area, right, by using dry etching process, right. And after dry etching, what you do is you can make the grating coupler. So, you want to couple using grating couplers, which is something we also discussed earlier, and etch 70 nanometers. Here we etched 220 nanometers for this device, and here we only remove 70 nanometers, right. So, that is this section, right, and once you and this section is defined during this step. So, by combining these two etch processes, you get this final device. So, what you are looking at the bottom is a scanning electron microscope image of this coupling structure. You have a grating fiber chip coupler. So, you can put your fiber here. So, light will vertically fall on this, and then it will be guided through this a taper, and then you will split the light here, and then you can combine it through this. Okay. And you can see here very nicely defined a slot waveguide. So, the cross section would look something like this, right. So, this is all silicon, and then you have air. So, now the question is how are we going to characterize this, right. So, you want to know whether the light is confined in this slot or not. One of the problems that we have, right, when we work with longer wavelength is you cannot image this, right, and the limit is very rather small. So, you are talking about light confined in 100 nanometer slot. This is sub wavelength confinement that you are looking at, and imaging it is not going to be easy. We need to find interesting way of characterizing whether we excited this particular mode or not. How do we confirm, right. So, when I do a measurement, I will get some spectral response, no doubt about it. So, light is going to couple through, and then you will see some light coming through, but then how do you confirm that this light is indeed confined between these rails and not propagating as a super mode, right. In a directional coupler we have this super mode, right, it looks like a directional coupler. So, how do you confirm that the light is not propagating as a super mode? How do you know that it is propagating as a slot mode? So, we need to know that, right. So, how do we do that? We cannot image it, we cannot look through the camera, because the wavelength that you are using is beyond, let us say, the camera resolution, right, both in terms of spectral and also spatial. How do we do this? So, we need to rely on the spectral characteristics. How do we relate the spectral characteristics to our waveguide characteristics? Let us look at that. So, when you take a simple waveguide, so we can change the waveguide width, and this waveguide width will have different effective index. So, this is a typical waveguide dispersion, right, and for a certain width you will have different refractive indices, right, the effective index and also group index. So, this is something we can calculate, right. I think you all agree that this is fairly easy to calculate the effective index and group index of a given cross section. And now we can make a very simple cavity here. ring resonator here, and we know this ring resonance depends on the effective refractive index, right, and the radius is fixed in this case, right. So, the effective index of this ring is going to determine the resonance here, right, and we can go back and then see what is the spectral response here, right, and from the spectral response we can find the group index, right. So, the free spectral range we know, right, coming from the measurement, and use that free spectral range, lambda we know, r we know, right. Then we can find the group index, and from this group index we can relate it to our simulations here, whether this is correct or not, right. So, I think this is a fair method of validating whether we have excited the slot mode or not, right. So, this is the confirmation of this particular excitation process. So, you can make a simple test structure like this. So, we have the grating coupler here, these are all the input and output couplers, and this is our wire to slot couplers that we had, and now we have a ring resonator. So, this is again a ring, but in this case slotted ring, right. So, you can see here there is a gap, right. So, this is slotted ring, and now this fabricated device is put through the characterization. That means, you are going to put the light in input and then you are going to measure what is coming out, and this is what the spectral response is, right. So, you have for varying wavelength you have this resonances that we have, right. So, each one of this is a resonance wavelength that we have. So, from the resonance wavelength we can find the free spectral range, right. So, we know the free spectral range, we know the lambda, we know the r, the radius of this ring, in this case 59.8, and the group index is 3.17 is what we measure out of this device, and actually the simulated group index is 3.12, which is very close. So, this is close to what we actually expected, right. However, your refractive index for a wire waveguide will be much larger. So, we do not have to worry that this is a wire waveguide mode. So, this is indeed a slot waveguide mode, and we have excited the slot mode, and this is the confirmation of that. Okay, so, we have confirmed that the light is now sitting between the rails, right. So, we had these two rails and the light is sitting between the rail now, right. So, two silicon waveguides and sitting in air, and we have confirmed that as well by looking at your group index. So, let us put it to use now. So, how are we going to do that? Let us put some analyte on top of this, right, and then see whether they interact with this analyte, and this interaction should result in some change in the spectral response, right. So, there are two examples that we are going to take here. One is a concentration measurement for potassium chloride here you have KCl. So, when you change the concentration of KCl, right, there is a shift in the refractive index, and this shift in the refractive index as a function of concentration can be plotted here. So, the red curve that you see here is from the slotted ring, right. And then the quality factor, right. So, the quality factor is nothing but delta lambda over delta lambda, right. So, this delta lambda is measured, right, because this delta lambda, if you remember, depends on the loss in the cavity, right. So, that Q factor remains more or less the same, right, there is no change in the quality factor. So, the slotted ring, you know, the refractive index is changing, right. So, the refractive index change we see here, but we are confirming it with some Abbe refractometer. So, this is a standard way of measuring the refractive index. It's a bulk tool, right, that we use as a reference, and that shows an excellent agreement between the measurement that we do on chip using this slot ring with a bulk measurement. So, this confirms that whatever refractive index change that we are measuring is actual change in the refractive is change in the concentration of the analyte that we have, in this case potassium chloride. So, this confirms refractive index measurement. So, we have concentration measurement approved by this technique. So, then we want to do even more. So, let us look at glucose for example, right. So, we took various concentration of glucose. So, these concentrations are reasonably high, but this is just for proof of concept. So, you take a glucose here and then you again run it on top of the ring. Right. So, here what we see is a change in the refractive index, right. So, the refractive index or your wavelength is changing because of refractive index, but what we also see is the Q factor is reducing, right. So, your quality factor is reducing while your shift is positive. So, this quality factor change is attributed to your absorption. So, the light is getting absorbed because of the glucose concentration. So, now you can see the wavelength change is coming from your concentration change, while your Q factor change is coming from absorption change. So, simultaneously one can measure density change and also absorption change. So, you have the concentration that is giving two different reactions to this. So, by using these two different quantities you can firm up your actual concentration that is measured. So, the final concentration that you can do now got two quantities, the two parameters, right, in order to arrive at the glucose concentration. So, normally you will have less number of equations to solve more unknowns, but here you have one unknown, but you have two knowns, right. So, they are all related. So, by using this you can get much better sensing modality. So, with that we can say that by using photonic integrated circuits, by engineering the light propagation through the waveguides, and in this particular case by using a slotted ring, right. So, by using a cavity, but it is not any other cavity, in this case it is a slotted ring cavity where you can confine the light between the rails. By using this you can efficiently, effectively measure concentration change, and also you can measure absorption change. So, both could be done simultaneously, which gives us more versatility, right, in exploring different kind of sensing analytes, right. So, with that I would like to summarize whatever we discussed on the sensing part, right. I hope you will all agree that this platform is very versatile. You can do lot of interesting things by exploiting this particular waveguide platform for various application. Particularly sensing is very vibrant. It is just up to us coming up with various strategies. I hope this should have given you some insight into what you can do with it. I hope you will use this and build interesting sensors out of this understanding. Thank you very much for listening.